Welcome back to Maths with Mrs. Jane. Now that I've done my series of videos about limits, I wanted to revisit the topic of sketching rational functions. And I wanted to do another example just to point out how useful our limits knowledge is and how important it is, but also to talk a little bit more about asymptotes and asymptotic behavior. Some students have the mistaken belief that an asymptote is a line that the graph will never touch. Now, that is true in the case of a vertical asymptote. A vertical asymptote occurs when the function is not defined. So the function will not cross a vertical asymptote. That is true. However, a horizontal asymptote, occasionally you will get a function that will cross it early on, so in towards the y-axis for smallish values of x, and by smallish values I mean not when x is tending towards infinity. So it might cross it, and then as x tends towards infinity or negative infinity, it will tend towards that line and not touch it again. I wanted to go through this example just to again point out that information about asymptotes, limits, and also to point out the process that we go through if we are sketching a function by hand. Obviously, these days we have technology that will do a very good job for us, but it's important to understand the calculus and the algebra behind what is going on. So doing a sketch by hand is an important skill to still have. The sorts of things that you need to be doing: finding your intercepts, finding your asymptotes and what happens around those, finding any stationary points, determining their nature, finding any points of inflection and the concavity either side of those, and then obviously popping all that onto a nice neat sketch. I do thoroughly recommend that you use a pencil when you are sketching, because if you do make a mistake, then it's easier to fix. I also recommend that you do a relatively large sketch. If you want to be able to show the information and be able to demonstrate the change in concavity, for example, you need to have something that is at least a decent size so that people can see what you're showing them. All right, so let's get started. Let's start with the intercepts. Okay, well, when x is 0, it's not defined. And we're going to get up to that in our next point. But we know that there is no y-intercept here. When y is 0, that means that the numerator will have to be 0. So x minus 1 is 0, so x is 1. So your x-intercept is 1, so the point 1, 0. All right, I like to do little headings like this as I go, by the way, because it helps me focus on what I'm doing, but also anybody looking at my work can see at each stage the sort of procedure that I'm going through step by step and know what I'm attempting to do at each stage. Okay, well, any vertical asymptotes will occur when the denominator is 0, when the function is not defined. Now, again, there's a little proviso here. We did do an example in a previous sketching rational functions where the denominator was 0, however, the numerator was also 0. That's called an indeterminate form. And when you worked out the limit, it actually existed there. So a vertical asymptote will occur when the denominator is 0 and the limit as you're tending towards that vertical asymptote from either side will be either infinity or negative infinity, or they're both heading towards negative infinity or both towards positive. All right. So we're not tending towards some hole in the graph like that. We're actually tending towards something like this. Yeah. So there's a difference. So this one here, I know that when I calculate my limit, as x tends towards 0 of this, I am going to get infinity or negative infinity. We'll do that in just a minute. So the vertical asymptote occurs when the denominator is 0. So x squared is 0. So x squared is 0. Therefore, x is 0. So that's a condition we need to have a vertical asymptote, that the denominator has to be 0. However, we also need to check what's happening as we're approaching 0 from above and below. So as x is approaching 0 from above, okay, what's going to happen here is the numerator is going to be negative because a small positive number, but -1 will be negative, and the denominator will be positive. So your y will actually be tending towards negative infinity. As x is tending towards 0 from below, well, again, the numerator is going to be negative and the denominator is going to be an extremely small positive number, because if you're squaring an extremely small negative number, you get an extremely small positive number. So in this case, we're also going to be tending towards negative infinity. So that is a vertical asymptote. Horizontal asymptotes, let's just have a think about this. Okay, as x is tending towards infinity and as x is tending towards negative infinity, we need to think about what this function is approaching. Because the denominator has a higher power than the numerator, we know that this function will be tending towards 0. Let me say that again. Because the power or the order of the denominator is higher than the order of the numerator, this function will tend towards 0. You can even see that if you split this up into an x over x squared minus a 1 on x squared, so this is really 1 on x minus 1 on x squared, that tends towards 0 as x tends towards infinity, and so does that. So this function will definitely tend towards 0 in both cases. We just need to think about, is it tending from above or below? All right, as we're tending towards infinity, what's going to happen here? Well, 1 on x squared will always be a tiny, tiny bit smaller than 1 on x. So this will always be a slight bit positive, so it will be tending from above. As we're tending towards negative infinity, then this will be negative, and when we're taking away this, it will be tending from below, because we'll always have a slight negative number there. So we've done our asymptotes. We've got a horizontal asymptote. We've got a vertical asymptote. Now, this is interesting. Have a look at this, just to point out the glaringly obvious. Our x-intercept actually occurs on our horizontal asymptote. That's okay, and we'll see what happens as we go through the process and find our stationary points, etc. We'll see how that can possibly work. All right, so our next step in the process is to find our stationary points. Okay, I'm actually going to use this version to differentiate. It's just easier to work with. So f of x was x to the -1 minus x to the -2. So f dash x will be negative x to the -2 plus 2x to the -3, which is -1 on x squared plus 2 on x cubed, all over x cubed, 2 minus x. Okay, it doesn't really matter what process you use. You could do your quotient rule, that's fine. However you do it, you should come up with this. Stationary points, you put the first derivative equal to 0. We should know that by now. So for this to be 0, the numerator has to be 0. So x is 2. Let's find what the function's value is when x is 2. So f of 2, we're just going to sub in. It's probably easiest to sub into this version in this case. So 2 minus 1 on 2 squared, which of course is a quarter. So we know we've got a stationary point at 2 a quarter. So we've found, and that's the only one, all right? Now we need to determine the nature of the stationary points and any points of inflection. There are two different ways you can spell inflection. I tend to spell it with a CT. Some people spell it with an X. I just prefer the CT, it doesn't really matter. To determine the nature of the stationary point, you can pick a point a bit to the left and a bit to the right and find out what the gradient is doing. However, we're going to want to find our second derivative anyway in order to find any points of inflection. So we might as well pop this x value into our second derivative, find the concavity there, and that will tell us what sort of stationary point that is. So we said that f dash x was this. Let's just go back to this line here. Notice that I'm using different versions of the formula depending on what is more suitable for me at the time. all right? It's perfectly okay to do that. So I'm wanting to differentiate this, so this is probably the easiest version to work with. So we're going to get 2x to the negative 3 minus 6x to the negative 4. Let's pop all of that over x to the 4th, and we're going to get 2x minus 6. You could do that if you like as 2 brackets x minus 3. That's probably a good idea to do that. Okay, so at x is 2, so f double dash 2 is going to be 2 times 2 minus 3 over 2 to the 4th. That is going to be negative, isn't it? Because you're going to get a negative divided by a positive, so it's negative. So we know it is concave down at 2 1/4. So it's going to look like that there. So that is a local maximum. Okay, let's continue on and we'll find our points of inflection. We'll just remember this has to transfer over to the next page. Okay, so we have our f double dash x is 2 times x minus 3 over x to the 4th. So finding any points of inflection, we're going to pop that equal to 0. For f double dash x to be 0, the numerator has to be 0, so x will be 3. The value of the function when x is 3, remember our function was f of x equals x minus 1 over x squared. So it will be 3 minus 1 over 3 squared, which is 2/9. So we have this point 3 2/9. That is a point of inflection. We need to just investigate what's happening to the concavity on either side of that. Now, over the page, when we were determining the nature of our stationary point when x was 2, we found that f double dash of 2 was negative. So it was concave down to the left of x equals 3. Let's find out what's happening to the right. To the right, when you sub it into here, you're going to get 2 times 4 minus 3 over 4 to the 4th, which will be positive. So it'll be concave up. So this is definitely a point of inflection. We have a change in concavity from concave down to concave up. What sort of point of inflection is it? Well, it didn't come up when we were finding our stationary points. So it's not a stationary point, so it is not a horizontal point of inflection. Therefore, it must be an oblique point of inflection. Okay, let's just collect all our information in the one place so that we can then start popping it on our graph. So we said we had an x-intercept at 1, 0. We had both axes were asymptotes. And we know the behaviour around those, what's happening, whether we're tending towards negative infinity or positive infinity, or whether we're tending towards 0 from above or below, that sort of thing. So that will come in play. We have a local maximum at the point 2 1/4, and we have an oblique point of inflection at the point 3 2/9. Now, just so that we know, 1/4 and 2/9, well, 1/4 is 9/36, this is 8/36. We're talking about numbers that are very close together. So we want to pick a scale that will enable us to show the shape of the function. So I'm not going to put 1 down here, or we're not going to see anything. Let's pop our asymptotes in first. I'm going to do them as a solid line to start with, and then I'm going to dot over it. So just bear with me for a minute. So we've got a vertical asymptote there and a horizontal asymptote there. Can't see that very well, but that's okay because I'm going to dot over it in just a tick. So we've got our vertical asymptote here at x equals 0. So that's x equals 0. We've got our horizontal asymptote along here at y equals 0, in other words, the x-axis. Now, let's choose a scale so that we can actually show what's going on. With our x values, we'll go up to, say, x equals 4. So we'll start with maybe x equals 1, 2, 3, 4. But with our y's, we want to put 1 way up here somewhere so that we can sort of demonstrate what's going on. Because if 1's up there, a half is there, a quarter is there. Let's plot a couple of points. So we've got, this is our x-intercept. The point 2 1/4 is our local maximum. The point 3 2/9, which is just a smidge below, is our oblique point of inflection. Now, how are we going to put all of this information and what's happening as x tends towards our 0 from above and below, how are we going to put all that together? Because as we've got there, we've got 2 asymptotes and 3 points. This is where your asymptotic behavior comes in. We know that as we're tending towards 0 from above, that the f of x is tending towards negative infinity. So we know that this part of the graph is tending towards negative infinity. And we know that that's a local maximum. And we know that at this point here, the concavity changes from concave down to concave up. And we know that as we're tending towards x equals infinity, we're tending towards this line y equals 0 from above. Now, I'm not particularly happy with the shape of that function, so I'm actually going to redo that last little bit, in fact, all of it, which is okay to do. That's why I suggest very strongly that you use a pencil. So we've got something like this, coming up to a local maximum. We're concave down, then we're concave up, then we're tending towards that line. That's acceptable, all right? Now, we don't have anything here, but this is where the asymptotic behavior really comes into play. We know that as we're tending towards x equals negative infinity, we're tending towards this line, y equals 0 from below. So we're coming up here. And we know that as we're tending towards x equals 0, where the function is tending towards negative infinity. So what we've actually got here, even though we've got no actual points in that section, we've got that kind of shape. And there you have it. It's not going to be perfect. It's not going to be suitable to read values off, but it gives us our basic shape of our f of x equals x minus 1 over x squared.